Students, today we are looking at simple harmonic motion. Simple harmonic motion. And what we are doing now is to give you a brief description of the types of motion. Later on, we shall be taking them one by one, and we shall be dealing with them into details. This motion we call simple harmonic motion is a topic on its own. But for now, we just want to show you what that motion is. That's all. And we shall be talking about that later. Now, the short form of simple harmonic motion is what we call SHM. SHM. So what is simple harmonic motion at all? Let me take a point P and call that point a fixed point. And I have a body. At this point, we call the fixed point. Now, the body moves away from this fixed point. And that body does so with an acceleration. Why? Because the body was initially at rest, and the body moved and gained a velocity. There has been a change in velocity, so the body possesses acceleration. Watch this. The body is going away from the fixed point, but its acceleration, I'm using A for that. Its acceleration is rather directed towards this fixed point. So strange. The body is moving away. This is the direction of motion. And yet, its acceleration is drawing or directed toward this fixed point. And let me say this. Force gives rise to acceleration. And so force and acceleration are in the same direction. And so what it means is that the force on this body is also directed in the same direction as the acceleration. So we have both the acceleration and the force directed toward this fixed point. And I repeat, the body is moving away from this fixed point. This is the direction of motion. And yet its acceleration is directed toward this fixed point. It means that the force on this body will also be directed toward the fixed point. What will happen is this. The body cannot fight the force. So the body moves to a point and will have to follow the direction of the force. In other words, the body will come back. Now when the body is coming back, they come back and then will bypass this point and go to the other side. And the moment it bypasses this point, this fixed point, and turns this direction, the acceleration will also turn, also to move in this direction. Do you know what is happening? The acceleration is always directed opposite to the direction of motion. Opposite to the direction of motion. So the acceleration is always directed toward this fixed point, no matter where you are, no matter where the position of the moving body. Not only that, again, the acceleration possessed by the body is directly proportional to the displacement of the body from the fixed point. Now, put the two together, and this is what we are calling simple harmonic motion. I will do just a brief explanation again, and then we move on. I have this point, P, and I call this point the fixed point. Now the body moves away from this fixed point, but its acceleration is directed opposite to it, towards the fixed point. Watch it. If the body has moved from here to there, this will be its displacement, and I'm using A to stand for the displacement. It has moved from A, which is the fixed point, to this point somewhere there, and it has gone through a displacement S. A displacement S. Now, if the acceleration is always directed towards the fixed point, always directed towards the fixed point. Secondly, if the acceleration is directly proportional to the displacement from the fixed point, put the two together and we'll call such a motion simple harmonic motion. And in fact, if you check it very well, I said because the acceleration is directed opposite to the direction of motion, the body is forced to come back. The body crosses this side to this fixed point to this side. Acceleration will direct it back again, and the body will end up doing this. They end up doing this. So in actual fact, simple harmonic motion is an oscillatory motion, but with certain qualities. And I repeat, simple harmonic motion is an oscillatory motion with additional qualities or additional properties. And what are they? One, SHM shows a repeated motion. It shows a repeated motion. 2, SHM shows a periodic motion. 3, SHM shows oscillatory motion. 4, the total energy of SHM is constant. If I don't want to use the word constant, we simply say it's conserved. When you conserve something, you are preserving. Nothing is taken away, nothing is added to it. So it remains constant. Again, the frequency of the motion does not depend on the amplitude of the oscillation or the motion. Students, I said we shall be dealing with this topic on its own. Don't worry. We will see this and we shall talk about this into details. But what I want to say is this. When we are talking about simple harmonic motion, all these things are embedded in the simple harmonic motion. Anytime a body is performing simple harmonic motion, you see the body showing repeated motion. You see it showing periodic motion. You see it showing oscillatory motion. And you see the body having its total energy conserved. And the frequency of that motion, again, does not depend on the amplitude. So you see, as I said, if you are to give examples of simple harmonic motion, then you'll be giving examples of motion that is to and fro, to and fro, to and fro. So let's look at the examples that we can give for simple harmonic motion. Students, with me on the table are some of the few examples and very important examples that we are going to give. They are important because These things you see here are the things that appear in your exams. In fact, when we are talking about experiments on mechanics, most of them are simple harmonic motion experiment. And we have these examples. Now, the first one has to do with a simple pendulum, and you can see it. Simple pendulum. Now let's see how it performs simple harmonic motion. And as I said, simple harmonic motion in actual fact shows to and fro, to and fro. So what we do is to swing it and then you leave it. Just displace it through a small angle and you leave it. And that is it. It performs simple harmonic motion. All right? The next one has to do with the spring. Elastic spring. I'll take the pendulum off and then I'll mount this spring on this stand. Can you see that? This is the spring, and the spring has been weighted or it has been loaded. It means something has been hanged on it. Now, we are going to cause this spring to perform simple harmonic motion. So what I will do is to displace this spring downwards a bit and leave it. And that is it. Please, if you should displace this one through a large distance, something will happen, and I will show you. And that is why it is always advisable to displace the load through a small distance. And I'm going to do that for you to see. Now watch it. I'm even afraid. Do you see what is happening? All right. All right. So to avoid this, it is always said, and that is what we expect you to do, that displace it through a small angle, just a small distance. Displace it and leave it. See how wonderful and how beautiful the oscillation is. Take note of this. Don't worry, we shall be doing this again under the topic SHM. Then we also have what we call a compound pendulum. We call this one a compound pendulum. It's just a meter rule with holes drilled along it. And most of the time, the holes are 5 centimeters apart along the entire length of the ruler. So what you do is to suspend this compound pendulum through any of the holes. And here we are. Now, I'm going to displace this one through a small angle and leave it. And it swings. Please, the displacement is always through a small angle or through a small distance. Just a small distance or small angle. And it is swinging. This is what we call the compound pendulum. Compound pendulum. We haven't finished. We have what we call the cantilever. Cantilever. And now we are taking our time to show you all this because almost all the practicals that, as I said, you do on mechanics, most of them are on simple harmonic motion. And these are the questions that you will see coming up. This is a cantilever. Now, cantilever is simply, again, a ruler. And of course, it should be a flexible ruler. Flexible one. Now, some section of it is on the bench, and the other section protrudes out of the bench. Now, normally, it is weighted. In other words, a load is hung here so that it will slow down the motion. You'll be counting, and you should be able to count how many oscillations. So we must be able to slow the motion down. So most of the time, the question will ask you to put something here, a load here, and they will specify the mass that you are supposed to put there. Even when they don't ask you to do that, you can still count. You can still count. Only that you do that with some difficulty. Now let's see what happens. I'm going to displace this one down slightly, and I will leave it. And then you can see it. You can see that. And that is to and fro, to and fro. You know what? The to and fro can be horizontal and it can be vertical. That is why when we're in school, and I don't know whether you are doing these days, anytime somebody is doing off in a classroom, we always say that the head is performing SHM. Somebody who is doing snuff is always like that. And that head performs SHM. Let's look at the other example. So here we are. A ruler mounted horizontally on two strings. And these two strings are held by two rotor stands. This arrangement is simply called a bifilar suspension. Now, we are going to cause this suspension to perform SHM. And watch me carefully. Watch my hand carefully. The way I'm going to set this to be in motion. And go straightly by that. I'm going to hold the two ends, and I will displace them in opposite directions. So I'm going to do this. In opposite directions. And I will leave it. And it swings. It swings like that. This is all about bifilar suspension. But I want to caution you here. I've seen students doing this. And that is extremely dangerous. This is what they do. They swing the whole meter rule and they leave it. Are you watching me? And they leave it. And this is what you see happening. This is wrong. This is wrong. This is not bifilar suspension. What you have to do is to displace the two ends in opposite directions, and then you leave it to swing this way. That is all. Students, I've cautioned you about the way you set the bifilar suspension to swing. I've cautioned you. Let's look at the next example. This is the last example that we want to demonstrate in this studio. I have a test tube, an empty test tube. I want this test tube to stand upright in this water. But watch it, an empty test tube. If I leave it, it falls. It falls, and water gets into it. Now, if I want to avoid the test tube falling, what I will do is to put something in the test tube. And when you do that, it is said that the test tube is weighted. The test tube is weighted, or the test tube is loaded. So when you load a test tube and you load it with the right amount of any substance that you put in, it can be a sand, it can be lead shots, or sand. If the right amount is put in it, let's see what happens. I will leave it, and the test tube suspends. Now, we call this a suspended test tube in a liquid. And here we are talking about water. All right, now we want this test tube to show simple harmonic motion. I hope you can see it clearly. What I will do is to use one finger, press the test tube down slightly, and leave it. And the test tube will pop up and down, performing SHM. So watch it. Can you see that? I did that slightly. I will do that again. And that is SHM for you. Students, we shall come back to look at the other types of motion. See you.